Hi. How many of you are familiar with Kotlin coroutines? Okay. So, as you may know, Kotlin coroutines has become a stable feature in Kotlin 1.3. Since then, we could finally get rid of the experimenter flag and dive into the world of concurrency. However, coroutines are not just about async and launch coroutine builders. There are still some experimental and obsolete declarations which may get changed or redesigned in the future. My name is Iveta. I am an Android developer at STRV in the Czech Republic in Prague, and I will guide you through this forthcoming part of the coroutines API. Some of you might be wondering why you would consider using coroutines if we have threads. What is the key difference between coroutines and threads? To answer this question, we need to go deeper to see how threads work at the very bottom level inside of our CPU. So this is our CPU, and let's say the CPU has 4 cores, so it's a quad-core CPU. We can think about each core like a worker, and each worker does what the operating system tells him to do. So the operating system is like a boss who manages all co-workers. Threads are like sequences of commands given to cores. You can imagine them like assembly lines by which some products are delivered to workers to process. However, our workers are not the only one busy at this moment. Our boss, the operating system, is also fully included in the process. He has to manage all threads and take care of scheduling. Last but not least, threads are expensive. On JVM, each thread takes around 1 megabyte of memory. Now, when we hopefully understand the general purpose of threads and cores, it's also important to understand difference between physical and logical core. A physical core is kind of what it sounds like. It's physically on the CPU, is like the hardware of the CPU itself. A logical core is like a code. It exists in a computer, but it's not bound to any particular hardware. The amount of logical cores expresses how many threads we can start at the same time. So if we have a computer with 4 cores and we can run 4 threads at the same time, we have 4 logical cores and 4 physical cores. But if we have a computer, if we have a CPU with 4 cores and we can start 8 threads at the same time, we have 8 logical cores, but still just 4 physical ones. Now, what happens if we have more logical cores than physical cores? You can think about a situation like when a worker is responsible for 2 assembly lines. He cannot take care of both of them at the same time. Let's say he starts processing products from the first line, but then suddenly something happens, products are over, they are waiting for more products, something got stuck, whatever that makes the worker unable to work on the first line anymore. But at the same time, products for the second line may be ready to process, so the worker can take advantage of this gap, and instead of waiting until the first line is ready, he can switch to the second line and process his products from there. When he finishes his work, he can check if products for the first line are ready, and if they are, he can switch back and complete his work there. Now, all work is done, the boss is happy, and the worker can go home earlier. The situation which we have seen at the beginning, when all workers are working at the same time and each of them is responsible just for one line, is what we call a parallel operation. But as we have seen, a core itself cannot work on multiple threads. If there are more threads to process, the core needs to switch among them. This switching operation is what we call a concurrent operation. So it kind of pretends to be a parallel operation, but in reality, all tasks are not executed at the same time, they are executed concurrently. And speaking about concurrency, we are now ready to start talking about coroutines. Conceptually, coroutines are like threads executing work concurrently. But unlike threads, coroutines aren't necessarily bound to any particular thread. A coroutine can start processing on one thread, then suspend its execution, and resume on another thread. The most important thing about coroutines to remember is that while they are suspended, they don't block the current thread. When a coroutine hits a suspension point, the thread is returned back to its pool, so it can be used by another coroutine or by another thread. Coroutines are managed by the operating system. They are managed by the Kotlin runtime. They are a language feature. The operating system has to care neither about coroutines nor their planning. Coroutines handle all these tasks by using cooperative multitasking. When a coroutine reaches a suspension point, the Kotlin runtime will find another coroutine to resume. Another thing about coroutines is that they take just a small amount of memory, just some bytes. And because of that, you can start so much more coroutines than threads, which gives you a very high level of concurrency with very small overhead. And now, prepare yourself to do an experiment which result should be a hamburger. During my high school, I worked in a food stand at the swimming pool during summers. And because I had a really good time there, I decided to use the analogy of ordering a hamburger in our hamburger stand to explain the experimental coroutines API. So when I started working there, I was the only employee of our hamburger stand. To prepare a hamburger, I used knife to cut vegetable, a deep fryer to fry meat, and a microwave to heat a bun. Yeah, don't buy hamburgers in cheap hamburger stands. Because I was new and without experience, I did everything sequentially. So I took an order, I cut vegetable, I started frying meat, but I stayed close to the frying machine because I was scared that if I did anything else, the meat would get burnt. When meat was done, I put it aside and I did the similar process with a bun. I put it in the microwave and I was waiting near the microwave until it was warm enough. With all ingredients prepared, I just mixed them together and I served a hamburger. Let's rewrite this process by using coroutines. We start a coroutine with representing name Iveta, and inside we run a function make hamburger with an order list as a parameter. Inside of this function, for each order, we just get vegetable, get fried meat, get heated bun, and we prepare a hamburger from received entities. Each function is executed sequentially. Each of them needs to complete before moving to the next function. Let's run this code. And as you can see, each function is executed sequentially. First, cut vegetable, then fry meat, heat bun, prepare hamburger, and serve the hamburger. After a few days of practicing, I became a professional hamburger maker because I was able to fry meat and heat a bun at the same time because I could estimate how much time each process needed. So I took an order, I cut vegetable, I started frying meat, but I didn't have to stay close to the deep fryer. Right after, I could put a bun in the microwave, and then I was waiting until either the bun or the meat was ready. If the bun was ready first, I took it, and later, when the meat was ready, I took it as well, and with all ingredients prepared, I just mixed them together and served a hamburger. To reflect this situation in our previous code, we need to change just a few lines of code. Here. We need to wrap functions fry meat and heat bun in async coroutine builder. The async coroutine builder returns deferred a lightweight non-blocking feature that represents a promise to deliver a result later. We need to call the suspending function await on the deferred object to get the eventual result. So we call both functions concurrently, and we prepare a hamburger when all ingredients are ready. Let's run it. As you can see, both functions, fry meat and heat bun, were executing concurrently on the main thread. When the summer holidays started, more people were coming, and I just couldn't manage the whole stand by myself. We needed more people and some hierarchy of responsibilities to handle long queues as fast as possible. So we hired more people and we created two roles, cook and cashier. The role of cook was taken by me and my friend Dominika, and to take care about the cash desk and taking orders, there was Lenka to help. We also needed to buy more appliances for each cook one, because otherwise we would have likely killed each other. So the situation looked as follows. Lenka took an order, and the first available cook, let's say me, received a command to process the order. In a while, Lenka took another order, and the first available cook, now Dominika, because I was busy with the first order, received another command to process new order. But then both cooks became busy. There were no more cooks to process more orders, so Lenka had to stop taking more orders. She needed to suspend until at least one cook became ready. And so now we have more coroutines. We have people, we have Lenka, me, and Dominika, and we need to find a way how these coroutines can communicate. And that's exactly channel is good at. So our first experimental declaration, channel, serves as a communication medium which provides a way to transfer a stream of values among coroutines. A channel is conceptually very similar to blocking queue with one key difference. Instead of blocking put, it has suspending send, and instead of blocking take, it has suspending receive. A channel implements two interfaces. Sender channel, represented by actor, which we will discuss later, and receive channel. Receive channel represents a producer-consumer pattern. So a producer produces values and sends them to the channel, and a consumer consumes values from the channel. So you can imagine a channel like a tube or box where all these values are stored for some time. Multiple coroutines may receive from the same channel, distributing work among themselves. Each coroutine will have its turn to receive a value from the channel. Same on the opposite side. Multiple coroutines may send to the same channel without worrying that one coroutine would exceed the whole channel's buffer. Because of that, we can rely on the fairness of channel while implementing both fan-out and fan-in logic. Work will be every time distributed fairly among all coroutines. So now let's suppose that Lenka represents a channel, that she is a communication medium between people asking for hamburgers and cook processing orders. At the beginning, all coroutines are active. There are no people asking for hamburger, and so no orders to be processed. The first person comes and asks for a hamburger. The first available cook, me, receives a command to process the order. Therefore, I become busy. So once again, all active, first order. I receive a command to process the order. So I became busy, so I need to suspend so that I couldn't take more orders until I process the one which I currently have. In a while, Lenka takes another order, and the first available cook, now Dominika, because I'm suspended, receives a command to process the new order, and she suspends as well. As a result, Lenka needs to suspend too and stop taking more orders because there are no more available receivers. However, when I finish my task, I can let Lenka know that I'm available And she can become active and start taking more orders, which I can process. But as you may know, nothing lasts forever, neither does our working day. So in the evening, Lenka just closes our stand, and so the channel gets closed, which is a sign for the people that it's the time to go home, and also for cooks that they are free of work and they can go home too. Let's check how we can implement this situation. We create a channel as a communication medium between people and cooks. We launch a coroutine representing people, which is responsible for sending orders to the channel. When we process all orders, we cannot forget to close the channel, because otherwise our program would be in a suspended state and it would never finish. As a next step, we launch 2 coroutines representing our cooks, and we implement the fan out logic. That's the one where multiple coroutines may receive from the same channel. Inside of both suspending lambdas, we pass the channel as an input parameter so that both cooks can work with the same channel. In make hamburger function, we get orders from the channel by using a for loop, and we process each order by the way we have seen before. There are 2 ways how we can optimize this code. The first optimization is that instead of creating a channel implicitly through its constructor, we can take advantage of produce coroutine builder, which launches a new coroutine to produce a stream of values by sending them to a channel, which is then returned as receive channel. The main advantage of this approach is that the channel is automatically closed after finishing the lambda inside of the builder. The second optimization is that instead of the for loop, we can use consume each extension function, which does almost the same. It creates a for loop somewhere under the hood, but it's not totally safe to use it with multiple receivers. With the for loop, when one receiver fails, the second one is still able to process the channel, while consume each always consume or close the channel on its normal or abnormal completion. And we don't want to close the channel if an error occurs, because if one cook makes a hamburger with ketchup instead of mustard, it's not a reason to close the whole stand. That's why we rather leave the for loop here. Let's see if it works as expected. The first order was taken by me. The second one by Dominika, because I was busy with the first order. And right after I finished my order, I started processing the third order. Work was divided equally. First order was taken by me, then Dominika, me, and the next one would be taken by Dominika. If we assume that making hamburger would still take the same amount of time, that each cook would process the same amount of orders, thanks to the fairness of channels. Channels offer flexibility in terms of how many messages you want to keep inside before suspending by specifying a buffer type at its constructor. Rendezvous, I have no idea how to read this, is a default channel type, is a channel without any buffer. That's why it suspends until both receiving and sending coroutines are ready to transfer data. Conflated channel is a channel with fixed buffer size 1. So if a receiving coroutine cannot keep up with the producer overrides the last value in the channel. And when the receiver is ready to take the next value, it will take the last value sent by the producer. And buffered channel is a channel with a specified buffer size, capacity, and unlimited, as its name says, creates an unlimited channel, but by using this kind of channel, you lose automatic backpressure propagation. Now let's introduce a regular Sunday situation. A huge group of people comes to the stand and they start asking for hamburgers all at once. So it looks like, I want 1 hamburger, and I want 3 hamburgers, and you know what, I don't want 3 hamburgers, I want just 1 hamburger, and I change my mind, I don't want any hamburger, and etc. Lenka needs to calculate the final number of hamburgers, which is not a trivial problem because this number can be changed asynchronously by many people. And to be honest, Lenka is not the most patient person in the world, so without any help, she would either make a mistake or get angry. Fortunately, Actor is here to save the day. Our first obsolete declaration channel, Actor, is the second type of channel implementing sender channel interface. You can imagine Actor as a mailbox. It receives messages and it processes them as it's needed. However, the real power of Actor is to serve as a synchronization mechanism for coroutines in case you want to access a shared mutable object among more coroutines. The first step of using Actor is to define a class of messages that the Actor is going to process. And Kotlin CL classes are great for this purpose. So we define a quantity counter message with increment quantity message to increment quantity, decrement quantity message to decrement quantity, and get quantity message to get the amount of quantity. Completable deferred represent a single value that will be known in the future, and here we use it as a communication primitive to send the response back. We define an extension function that launches an actor by using actor coroutine builder. We need to specify our shared mutable object that's gonna be saved by the actor and actor's reactions on this object based on a message it receives. As a next step, we need to simulate the massive order, the one where more people come and they start asking for hamburgers all at once. So we launch as many coroutines as people we have to allow to act them concurrently, and each person will ask request time to either create an order or cancel an order. The main code is then straightforward. We just create quantity counter actor. We run a massive order with 8 people where each person can ask 3 times to either create an order or cancel an order. We get the final number of orders. And when the actor is no more needed, we cannot forget to close it, no matter if it's created through the constructor or by using actor coroutine builder. That's important difference between produce coroutine builder and actor coroutine builder. And as the last step, we just load the final number of orders and we process each order by the way we have seen a couple of minutes ago. So let's run it. We had a group of 8 people where each person could ask 3 times, so that's 24, so the first number is correct. But apparently this group wasn't as hungry as they thought because at the end they decided to take just 9 hamburgers. 9 is the final number of our shared mutable object saved by the actor. And the rest of the output is just what we have seen. By the end of this story, let's make it perfect, because in reality it wasn't important at all which appliance was used by which cook. I didn't have to work strictly just with the microwave number 1 and with the deep fryer number 1. We just wanted to make a hamburger as fast as possible, that's all. So when I wanted to hit a button, I could actually decide which microwave I would use. And of course, I decided to use the one which became available first. Our last experimental declaration, select expression, makes it possible to await multiple suspending functions simultaneously and select the first one that becomes available. It works like a when statement, but for channels and different values. From a bunch of channels and different values, it selects the first one that is ready. By ready, I mean either channels ready to receive from, So by using a select expression, you can actually receive from more channels at the same time. Or actors ready to send, or the first deferred value object that becomes with result. Right now, we are going to focus on actors ready to send, but the implementation for the rest would be the same. The situation is getting a little bit more complicated right now because instead of a select expression, or except for a select expression, we will need to use also channels and actors. So if you have some energy left, now is the right time to use it. We need to represent our appliances like actors. Let's focus on microwave and make it clear why. The case of deep fryers is the same then. We have to think about microwaves like shared mutable objects. A microwave is accessible by two cooks or two coroutines, and we need to synchronize this access because no microwave can be used by both cooks at the same time. A microwave actor suspends while it is hitting a bun, which is simulated by calling the suspending function delay. And while it is suspended, it's forbidden to put another bun to the microwave until the one which is currently heating is not warm enough. The message type this actor is going to process is microwave request, which is a simple data class holding a bun, which we need to heat, and a channel, that serves like a communication medium between microwaves and cooks. By using the channel, the microwave actor can let cooks know that the bun is ready. It's like the beeping sound which a microwave makes when time is out. On the other side, we wrap both actors in a select expression, which selects an actor that is first ready to accept or send a microwave request. When a request is sent to the channel, we wait for a response which will be delivered by the channel, and we return the heated bun. So the grand finale. So let's focus on Dominika and her third order. She cuts vegetable, she started frying meat in the first deep fryer, and she started heating a bun in the second microwave. She didn't go on a straight line. In both cases, she selected the first device that became available. When the meat was fried, the deep fryer sent a message that its work was done, and the same with the microwave. With all ingredients is prepared, she just mixed them together and served a hamburger. Since that, our hamburger stand was perfectly organized, and we were able to feed so many hungry people. And that's the end of our experiment. Just keep in mind that all this declaration may evolve in the upcoming updates of coroutines API with potentially breaking changes. So although they are super powerful, think twice before using them in your project. Because you can easily end up like me 2 days ago when I did last adjustments for this presentation, and I marked it as done, like I was finally satisfied. So because it wasn't too late, I decided to check some news, some reading for the night. And I saw that the new experimental declaration called Flow, which supports cold stream because channels are hot by default, was released. But Flow is currently at Alpha 2, and it doesn't change anything about previous entities, so my presentation is still relevant. But that's really exciting announcement you can start working with. This is the link for all code examples you could see, and that's it. So if you have any questions, Hi.
Thank you. I really enjoyed it, and I really liked the hamburger stand because it was very clear to me what you were talking about. I was just wondering if you had like an example of where you might use this in programming.
Okay. Like we use channels for API calls because we kind of defined, let's say, like a network state, which is kind of how to say, that is used frequently in Android development. That you kind of wrap each call in a network state and you return if it's loading, if it's successful, or if it's failed. And we wrap it by using a channel. It was kind of handy. And I use actors in a service because I didn't want to use an intent service, which is like synchronized by itself. I wanted to use normal service, let's say, and I needed kind of like synchronized access to this service. So I send each request through the channel, which makes a kind of a queue for me. But to be honest, I have never used select expression, and I don't know where I would use it. Probably if I have two API calls and I would like to get the first answer. But to be honest, I don't know what happens with the second call then. So that's it. And flow, like the new one, I don't know if I can say it in a loud voice, but maybe that's a good replacement for RxJava because it should work like Flowable.
Thank you. Any more questions?
Okay, so if you don't have more questions, thank you for your attention, and I hope you liked it.